In the last class, we have seen how the Fourier series or the sine and cos function can represent the L2 function. Let's take some example in this case, what we call is a Fourier example series. First, let's recapitulate the definition of Fourier series. Let f of x be a function in L2 in the interval minus pi to plus pi, then it can be expressed as a sum of sine nx and cos nx, and an and bn are coefficients. The coefficients of the coefficients a n and bn can be determined by taking the dot product of the function with the basis function, that is cos nx and the sine nx, that is an equal to dot product of f of x with cos nx, that is expressed as an integral minus pi to plus pi f of x into cos nx dx for n greater than or equal to 0. Equal to 0 corresponds to the constant or the mean of the function in the interval. The coefficient bn's are given as integral minus pi to plus pi f of x sin nx dx for n greater than 0. Before going into actual example, let's look at the plots of sin nx and cos nx is very similar, except that it is phase shifted by pi by 2, otherwise it would represent exactly similar function. Here I have plotted function for x is equal to only from 0 to pi, not in the negative axis, simply because one can easily construct sin nx given this function in the 0 to pi, because sin nx functions are an odd function, which is to say that sin minus x is equal to minus sin x. That holds for all the basis element, and one can easily reproduce the function in the negative axis. So let's look at the first sin x, which has two zeros on the boundaries, and there are no roots in between. Now when you have a sin 2x, it has one more zero in the inside the domain, and when we go on we get more and more zeros. For example, sin 3x has two zeros other than on the boundary, and we get higher modes, what we call, get more and more zeros or more and more modes inside the our domain. So this is essential to have these modes to represent the functions which are highly fluctuating. If the function is not fluctuating, then or they are slowly changing, then it can represent with the smaller values of n. If the function is fluctuating rapidly, then we need more and more n. Also, there are some cases even simple function requires a large number of modes. So we will also look at those examples. So as we go along, we get more and more wiggles, and these wiggles would essentially help us to represent the function which has a higher variation in the. For the first example, let's take a step function or the function which takes the value plus 1 when x is greater than 0 and minus 1 when x is less than 0. That is from minus pi to 0, it takes minus 1, and from 0 to pi, it takes the value of plus 1. The first thing to ask is whether this function is L2. Naturally, it's a finite function, and a constant takes two separate values, and it is integrable. So it is a L2 function. Of course, there is a discontinuity here at x is equal to 0, but we have said nothing about discontinuity. As long as it's a L2 function, it is sufficient for it to represented by the sine and cos. So piecewise discontinuity does not affect the L2 space. So all the functions which are discontinued piecewise, if it can be integrated, across, then it can be represented by sine and cos. Produces some artifact that we will look at later and try to understand them. So we have to simply compute the coefficient ans and bn. Let's first compute the a0, which is constant, which is this 1 by pi is a normalizing factor. Other than that, you have a integral minus pi to plus pi f of x dx. Since the function take two discrete value, minus 1 and plus, we split the integral from minus pi to 0, that is the function value is minus 1 integral dx plus 0 to plus pi, the value of function is plus 1, and the integral in this is 0 because they are exactly opposite to each other and adds to give 0. Because we don't need to do all this calculation to show that it is 0. We know that the step function which is provided to us is an odd function. That is, it flips the sign when we change from positive value to negative value. And when we have an odd function which is integrated in the symmetric interval around 0, then we would get the value 0. So we also have to use such kind of an understanding to reduce the algebra. But here I am explicitly showing most of the time we should not be doing calculations like this. It is sufficient to say that it is a odd function and the integral across the 0 with the symmetric interval should give the result of 0. Let's calculate the an coefficient which corresponding to the basis cos nx. Again, we integrate because function takes the two discrete value, we split up the function in two regions, the minus pi to 0. The integral simply becomes the cos minus cos nx, and from 0 to pi it becomes plus cos nx. This integral also becomes 0. You can no need to do this calculation. We know there is a minus sign here and there is a plus sign here. They are exactly opposite to each other and they would cancel out. This is also again same reason that we have an odd function f of x which is multiplied to an even function sin nx. Sin nx is an even function because it does not change its value when you change from positive side to negative side. That is cos x is also equal to cos minus x. So product of even and odd function is an odd function, and when you integrate it across the 0 with the symmetric interval, you would get the integral 0. Again, we should not be doing calculations like this. Intuitively, one should be able to tell that this should be 0. Let's coming back to coefficient bn's. They are obtained by multiplying by the sin nx. Now we see that sin nx is an odd function, and our function itself is an odd function. So product of two odd functions should be even function. So it is sufficient to take the integral from 0 to pi and multiply it by 2 because it is now an even function, and integrate. One can integrate sin nx because of the nature of the sign. We know that this behaves differently when you have n is equal to even or n is odd. So when n is odd, we get the value of this integral to be 4 by 2 pi, and when is even, it becomes 0 because the function is equally distributed around the x-axis, and the values on the upper axis it get completely cancelled by the values in the negative axis, and then we get the integral 0. So now we have all the coefficients. Let's try to reconstruct function with coefficient put in. F of x is equal to, we get 4 by pi sum over n. N takes only odd values. For all even values, we have a coefficient of sin nx is 0. We also have all the coefficient corresponding to cos 0, and the constant term a0 is 0. We can even write it in a more compact manner. We can write it as a 4 pi sigma n is equal to 1 to infinity 1 by 1 is 0 to n plus 1, and then sine 2n plus 1 x. So this would produce only odd terms. All the even terms are automatically getting cancelled. Let's look at this function and see the plot. We see that when the first term is included, it is only sine x. The sine x is nowhere representing a square wave, but as we add more and more terms, it takes the real shape of the function given to us. Let's look at this animation. We see that as we take larger and larger n, we come closer to the function given. The error becomes less and less as we take more and more terms. And we also notice there are some wiggles which don't seem to die off even if we take large and large terms. And you see that these wiggles essentially accompanies with the discontinuity in the function. So we'll come to this little later and try to see what is really happening. This is what we have. Let's play it again, and you see that as we take large and large term, it matches with that original function which we want, and we have taken nearly 100 terms here to reproduce the function. It is always not necessary. The main advantage of series is that it can be understood only with a few terms. In addition, it helps to us to solve the problem with the expressed in terms of some basis element. Basis element have a nice properties and which helps us to solve a given problem. Let me stop here and give few more example in the coming videos and try to demonstrate the power of the Fourier series.